The following examples all ask us to identify all complex zeros for the given polynomial function. Something to keep in mind, though, is that the real numbers are actually just a subset of the complex numbers. So we can represent a complex number in general as something of the form a plus bi, where it has a real component and an imaginary component. That means we can represent a real number in the form a plus 0 times I, meaning it has some real component, but its imaginary component is just equal to 0. So a question that asks for complex zeros means we want to find the zeros of that function. Our results may be complex numbers, or they may be real numbers. It just depends on the given situation. In example 3, we have a problem that in example 2, we tackled a similar version, where we had something of the form x squared plus a, and we applied the quadratic formula. If we have something of this form, though, we can take a faster approach by just setting that expression as it's given equal to 0. In this case, we would subtract 100 to the other side, and then take the square root of both sides of this equation. That would give us x is equal to the square root of negative 100. But whenever we take the square root of both sides of an equation, we need to introduce that plus or minus notation. In this case, then, that would give us plus or minus 10i as our two solutions. So in this case, we have two complex zeros for f of x, 10i and minus 10i. In example 4, since we have a trinomial, we have to apply the quadratic formula. So this would be 14 plus or minus the square root of negative 14 squared minus 4 times 1 times 65 all over 2 times 1. This would simplify down to 14 plus or minus the square root of negative 64 divided by 2, or 14 plus or minus 8i divided by 2. Keep in mind when we're working with the quadratic formula, we need to get down to this phase of that problem before we start reducing with the denominator. So this value in the denominator needs to be able to reduce with the term before that plus or minus symbol and after. So now that we've reached that point, we can divide all of these values by 2 to get 7 plus or minus 4i. That means we have two zeros in this case, 7 plus 4i and 7 minus 4i. Our approach to example 5 would be similar. We would apply the quadratic formula again. Which in this case would reduce down to negative 8 plus or minus the square root of 384 all over negative 4. In this case, our value under the radical is positive, so we're going to come up with two real solutions. We can break 384 into the factors 64 and 6. Which means we can break that radical down into 8 times the square root of 6 all over negative 4. And then we can reduce with that value that we have in the denominator to get 2 plus or minus 2 root 6. In this case then, we have two zeros again. But in this case, they're both real numbers with no imaginary component. In example 6, again, we start off with the same approach. We'll end up with 6 plus or minus 80 all over 2. 80 we can break into 16 times 5, meaning we'll be able to rewrite this as 6 plus or minus 4 times the square root of 5 all over 2, and then we can reduce to get 3 plus or minus 2 root 5. Again, giving us, in this case, 2 real solutions, or 2 real zeros for this polynomial function.